Hello, this is the start of a new series of lectures that I will be giving on many different topics. The first topic is calculus variations. The target audience is an advanced undergraduate or intermediate graduate student in mathematics or physics that has familiarity with linear algebra and calculus and differential equations. So calculus variations, we want to find out, well, what is this? This first lecture is just to give a brief introduction. There will be more details in subsequent videos. The outline here is just to give a very brief history. There's many different sources to find out the history of this topic. It's very interesting. I'm keyed in mostly on some real world examples that might wet your whistle. Toward the end, I'll explain optimization of real valued functions on vector fields in Rn. But calculus of variations is a generalization of that, and that's the last topic and introduction to what that is at all and how it differs from optimization on Rn. General theory. So it's a branch of mathematics, and I've got here highlighted in blue. This thing right here is the main thing. What we're trying to do in calculus of variations is we're trying to minimize something called a functional. This functional is called J. It has an input Y, and there's many different kinds of Y's I'm going to put into this J. At J, I get a real number out of it, and I want to try to find the minimum. Could be maximum as well. But it's without loss of generality argument, you just change the sign of J and mins become maxes. So, but the key here is I'm minimizing something, and I'm going to do it subject to certain constraints on the inputs Y. So there's going to be a set that I'm minimizing over. And just a very few examples of what J of Y represents in the real world. J of Y could be the area of something. It could be the cost of something. It could be transit times, such as a boat crossing a river under a current with constant thrust. It could be action, which is a concept in mathematical physics. And there's other quantities in science and engineering which could be minimized or maximized. The history, it started a long time ago, really a long time ago, between 16 and 1700s. Initially with something called the Christochrome problem, which I think I will be presenting that later. And the key players were Bernoulli, Newton, and Leibniz. And it was a kind of a interesting little problem. No one knew how to deal with it, but it was the thing that started to really seriously spawn the topic of minimizing J's, where J's are more general things. So in the 1800s, there was some theory that was formalized by Euler and Lagrange, and that stuff was really important. We'll get to it. And then in the 2000s, when we're coming up to where we are now, the subject still plays a very key role in theoretical physics, classical mechanics, and even field theory in quantum mechanics. So let's do a few examples now. All right. So the first example here is something called the Christochrome, which is a minimum transit time problem. And the idea is this. So up here, look at this graph. Here's an x coordinate. Here's a y coordinate. And imagine that you take a wire and you bend it to have a certain shape. So here I'm drawing out this one in brown, and it has a very particular shape. And on that wire, I have a bead which slides with no friction along that wire. It will take a certain amount of time to get from this point A to this point B. Now, if you change the shape of that wire, it will take a different amount of time to get there. And just to be the thing that makes that point obvious is, suppose I took this brown one instead. I'm going to trace it out with my arrow here. Suppose it went along straight, and then it did a deep fall down to B. Well, if the curve was like that, it would take a very long time, and then it would fall. So that's not going to be a minimal solution. So somewhere in between, there's got to be one which is an absolute minimum. So let's just see what this entails. So the shape of the wire is given by a function y of x. So here's x, the shape of the wire is y of x. Transit time down here, transit time for a particular function y is the arc length element over the velocity over the time that it takes. Well, because y is a function of x, ds is given by calculus, and the top is this 1 plus y prime squared. And I have velocity, which is dependent on x, and that's given by basic physics as determined by a balance of potential and kinetic energy. Now, without going into great details, I've converted this time ds over v into this integral in x only from x equal to a to x equals b. And I'm going to convert use kinetic energy is equal to the potential energy for a particle starting at rest, and you get this term y squared on the bottom. So in the end, you have a formula. If I told you what the shape of the wire was, if I told you what y of x was, I would put it into this integral, compute it, and that would tell me how long it takes for that bead to follow that wire. You change y in here, and you get a different answer. And the question is, of all the y's that you can put in here, of all the shapes that you can make, which one minimizes the transit time? So that's the kind of, this is very, very much the nature of all of these problems. They're typically integrals of things. This one arises from a very simple physics problem. Okay, what's another example? Well, bubbles happen to form shapes that minimize surface area. What do I mean by that? Well, so in this diagram here is x versus y versus u being the shape. So u as a function of x and y tells me the shape of this surface that's in white. And let's say I've got a wire around over here, and I've got a wire on the boundary down here around there, and then the soap film fills in this gap in here. The question is, what's the shape of the soap film? I mean, why not just have like a big blip over here where I'm drawing right now? Well, the reason, the physics behind this tells us that the shape is that which minimizes the total surface area that has the boundary values on the two wires. What that means in a calculus problem, I can write it out. If I know what u is, if I know the function u of x and y that describes this surface, then down here I've got the surface area element for that surface. This is from Calc 2. And the other thing I have is, so if I integrate that, and I'm integrating over the domain, which is this shaded thing here, D, that will tell me the surface area for any given u. And I have to minimize this integral, which has got partial derivatives of the function in it, and it has a constraint that u on the boundaries of D has to be a certain value g. That's the height. So here's a formula. S of u equals an integral, double integral in this case. And it's some well-defined integral that if I put a u in, I get an s out. If I put a different u in, I get a different s out. But all of them have to satisfy u equal to g on the boundary. Of all of those, which minimizes this integral or minimizes surface area? That would be the shape of the bubble. All right, what's another example? Harmonic oscillator. This is a very simple version of something we'll get into much more deeply later. But suppose you have here we have a mass M is drawn here as a M. There's a spring between it and a wall, and the distance from the center of it to the wall is going to be y at time t. The spring has got a constant k associated with it to determine its stiffness. And I can pull this out and it'll generally speaking vibrate back and forth. And we're going to say, well, let's try to say this is Teflon on Teflon. So there's Teflon at this interface, so it's effectively frictionless. And in that case, I can tell you this mass has got, way down here, it's got a kinetic energy of 1/2 mass times y dot, the speed, squared. And the potential energy for a spring is well known in physics. It's 1/2 ky squared. So a principle in physics is that physics likes to minimize something called the action. And in most cases, what the action is the kinetic energy minus the potential energy, not plus. So that would be total energy. This is different. This is kinetic minus potential. You integrate it in time, it gives you a value. So that has a formula down here of 1/2 my dot squared minus 1/2 ky squared. Of all of the y's that you can put into this integral, the question is, what y minimizes j? And the answer to that question tells you what the actual motion is according to a physical principle called principle of least action. In any event, this is another case where I have to minimize a function j, and it depends on a function y of t, which I don't know, and I'm thinking of all the possible y's I can put in here. How can I make this the smallest? And the answer to that question in physics is the actual motion itself, which minimizes j. Okay, another example. This is a common one. If you fly to anywhere in the world, any appreciable distances, planes will not travel like a straight line on a map. They'll generally look like a curve on a map. But what you do for planes is, like, if a plane is starting at, say, this point here on a globe to this point here, is you're traveling on part of a great circle. And the rationale for that is that actually that is the shortest that's the shortest distance of any curve that I could take going from A to B, and that is actually on the sphere. I wouldn't, so for example, I'm looking at this blue line here going from the initial point to the end point. If I took a sudden excursion, went way up and then came way back down, that would increase the length. You'd have to spend more time flying the plane, you'd expend more fuel, and that's not a good thing. So there's an interest to find what does the path of shortest distance between 2 points on a surface M look like. So in this case, I've drawn you a sphere rather, and I'm asking the question, given any 2 points on the sphere, what precisely is the shape that minimizes the distance between those 2 points? Now, if I'm going from a point P, I can parameterize any curve on the sphere by x of t. And I'm going to say that at time 0, it's at the point P, so that'll be this point here. And then at time 1, on some time scale, the position will be a point Q, which will be the end point. And the surface M is defined by whatever equation you like, but it's a sphere in this case, or it could be some other surface. Regardless of what it is, the arc length in multivariate calculus is given by you take the derivatives of the x, y, and z components of the vector valued function x of t, square them, add them together, integrate in time, and there you go. That gives you the length of that curve. From a calculus variation point of view, this is, you have an input function, which is x, and you get an L out of it, and I'm asking the question, what x minimizes L? So that's the question. And the answer to that is something called a geodesic. We'll talk about these things much more, but you get the drift. And here's another example, and you have to do an integral of some unknown function and try to minimize it. Fermat's principle in optics is another one. You have a medium. Here I've got a coordinate system x and y. You have a medium, and the red here is going to be the path of light when it hits the medium. So light actually bends in the medium in accordance with something called the refractive index of the medium, which could depend on, it could be the same all the way through, in which case this will be a straight line, or it could be varying anywhere all the way along this thing here, in which case it might be a curved path. But the Fermat's principle says that the path that light takes is the one that minimizes what looks like a minimum transit time problem. Again, it's the arc length element divided by the velocity integrated from the initial point to the end point. Here, the arc length is given by the magnitude of dx d lambda and some parameter lambda. And so that's ds. And then 1 over the velocity of the light in the medium is what the refractive index is. Why does this work? Who knows? It's a principle. It's been tested, and it works. But from a math point of view, it's saying, well, of all the paths x, what minimizes this last integral? Because if I can find the thing that minimizes this last integral, that will be the path that the light takes. So it's a minimum transit time problem. Again, input x, output t, subreal number of all of the x's, what one minimizes t. Another integral. What is minimization for functions on Rn? This is a really brief overview of things that we're not going to talk about, but I'm going to list all of them here in any event. There's a huge, you can take an entire course on this one slide. So the question is, here I have a function that maps from Rn to R and over some subset of Rn. And the question is on that subset of Rn, what's the minimum value of f for all the possible x's that are in there? If omega is the entire space, then it's called an unconstrained optimization problem. But more often than not, there are constraints on that define the subset omega here. A few examples of constraints, sets that are defined using constraints are omega 1, which is all of those paths, all of those x values that satisfy a collection of algebraic equalities. There could be one, there could be many equalities. But whatever they are, that's a type of constraint. Down below, if you look at this thing and you think about what I'm doing here, if I say I just goes up to 1, there's only one constraint. That's a typical Lagrange multiplier problem in multivariate calculus you would have learned. So that would be minimize your function of two variables over, let's say, g of x, y equals 0. And that, again, so that's typically solved using something called Lagrange multipliers. Here's a different kind of constraint. Maybe I'm optimizing or minimizing, maximizing f over a different set where the set is defined using a matrix AX, and that the values of all of the elements of AX lie between 0 and b. That's classically how constraints are defined in a topic of optimization called linear programming. These are linear constraints for a linear programming problem in which the objective function f is typically a linear function itself. That's just a huge topic. You could study that for a long time. Another way you can define your subset is through other means. In this case, I used a norm here. I used a norm in Rn. I said, look, we're only going to minimize f over all those x values that have a norm less than or equal to 1. Well, if this was an R3, that inequality would describe the boundary and interior of a unit sphere. So in this case, a compact set, and there's a theorem which says that if I maximize a real valued function over a compact set, it does attain its min and max. This is just meant to remind you or introduce you to dealing with minimization problems in Rn. And some of the theory that's used in solving these kinds of problems is also used in the more general case of calculus of variations where I'm minimizing a functional j. So what is the actual problem then? So here, this is the last slide here, and it's just simply to introduce formally what a calculus of variation problem looks like. So the first thing we have to do is we have to define something called a functional j. So a functional j is a function. So this is function al. It's a function that maps from some set A, it can be anything, into the real numbers. So perhaps I could say that A is a collection of shoes of different colors, and if it's red, the value is 1. If it's not red, the value is 0. That defines a functional on the set of colored shoes. But and we're not going to be using that kind of a set A, but that just illustrates how general this can be. So a functional, what you mean by it is it's a mapping from A to R. It associates a unique real number, j of y, to each y that is in the set A. So once you have that functional and you have this set A of things that you can try to min or maximize over, you can define the problem. You can say, here's the set, and I'm asking, what's the minimum of all the possible values that can be attained for those y's that are in the set A? And A is going to be called the admissible set. So it's going to be that. The thing that actually minimizes this, what is it? So it's going to be a y bar, some very specific y, or perhaps maybe more than one. But if there is a minimizer, meaning there's a y that I put in here that attains this minimum, then that's going to be called the argmin. So technically here, the argmin is the set of all minimizers. So there could be more than one, but it's the set of all y bars that actually attain the minimum value of j over the set A. This general verbiage here on this page, you can also use it to describe the previous slide. If you said, like for example, if I replaced j with f and omega is my admissible set and I'm mapping to R, then that technically is a functional from a subset of Rn into R, and it fits